So Mr. Sushil Mane is is working as technical director at Altair India Private Limited, Bangalore, and he has had a very vast experience in this particular field of CAE, and I believe more than 25 years of experience. I hope that this session is going to help everybody who is going to participate today. And like every time, there's a common instruction for all: do not switch on your videos while the session is going on, and also questions will be taken at the end of the session. So maybe you might note down your questions in your notebook and ask it at or during the Q&A session, or you can type it in the chat session. So we have around 250 people who have joined in. We'll wait for another minute and maybe then we can start at 5:20 as per our schedule. So this is about the expert today, and I'm now going to hand over it to Mr. Sushil Mane. So I request him to please take over the session.
Thank you, Professor Shirish Mane. Are you able to see my screen and hear me properly?
Yes, you are audible as well as your screen is visible. So we are all good.
Okay. Thank you. So just let me know when we have to start.
Yeah, so it's 5:20. I believe it's good if we start now as the schedule. We will not wait for people to join in.
Okay. Sure, we'll do that. So, a very good afternoon to everyone. As you see here, my name is Sushil Mane, and I'm the technical director at Altair Engineering India. I've been with Altair since a long time now, almost close to 19 years. And this has been my subject of interest, that is CAE, computer-aided engineering. Before I start my presentation, I would like to thank the management as well as Professor Shirish Mane for inviting me to present on this very interesting topic to a very interesting audience here. Coming from a variety of different colleges across India. I heard that there are close to around 300 plus people online now hearing this lecture. To begin on this topic, as the title suggests here, CAE for motorsport vehicles. So what do we mean by CAE? It is computer aided engineering, right? So it has all got to do with computer simulations that we are going to use to run engineering simulations for a variety of different products. For this topic, of course, we are going to talk about motorsport vehicles. But if you look back, people have been using this technology of doing engineering simulations for a variety of different products in different verticals, not just automotive, but even in aerospace, be it, let's say, shipping, healthcare, sporting industry, and so on, right? So if you look back, close to around 60 or 70 years ago, when mathematicians started modeling all these different physics, they were trying to model these different physics and try to build these models and run simulations, trying to mimic the actual behavior of these components that we see out there in real life, right? So the whole idea of running these engineering simulations was to basically try to mimic what we are seeing out there in nature or outside. And by doing that, the intention was to basically run these computer simulations very quickly on our computer systems and thereby reduce the complete product development time. That is one of the key benefits of running engineering simulations. That is to reduce product development time. Also, as you typically see, quite much before when we actually started designing and then building all these different products, there was a whole lot of time spent on designing these products, right? Because once you design, you have to do a lot of testing. And therefore, a lot of time was spent in testing all these different products. So with the advent of CAE, we were actually able to run these computer simulations for multiple different designs that we were trying to evaluate, and thereby the overall time spent on testing also got reduced, right? Not only just the time, but even the testing. CAE is a very powerful technique to design and simulate various different products that we design, right? So with that introduction, I'll just move on to the next slide here. I hope you can see my second slide. Here's the agenda. The agenda of my talk basically covers design and simulation using finite element methods. Of course, these finite element methods are typically being used in a variety of different FE-based solvers out there, including some of the solvers that we in our company use. And apart from that, there have been a lot of new methods being written recently on meshless techniques. So one of those meshless softwares that we recently acquired is a fantastic software. It brings a whole different dimension to product design, and that is something that I will be talking on. And then the other topics, simulation driven design process. So I'm going to talk about how you can actually drive the design by using simulation technology. This is one of the core, let's say, technologies that people have been using to reduce their product development process. And then, of course, you need to actually understand loads, right? Because those are the different conditions that you are going to apply on your product and then see the behavior of that particular design. So loads prediction, especially in the case of, let's say, automobile vehicles, is very important. And that we do it by using multi-body dynamics. So we'll just understand how you do that using MBD. Apart from that, we also do a variety of different physics simulations. Some of the core physics that we typically use, especially in automotive industry, is crash and safety, as well as fluid dynamics, that is called as computational fluid dynamics. So I'll be covering a few slides on how people have been using crash and safety or computational fluid dynamic simulations to design and validate their designs. Okay. And then finally, we'll have a discussion at the end with you all. So this is the agenda. So I'll now proceed to the next slide here. This particular slide is nothing but a video, and I would like you to now run this video so that you actually get to see how people have been using engineering simulations for a variety of different verticals, not just automotive, but all these different verticals. So this is a very nice and interesting video. So I'll just run that now. So I hope this nice and exciting video really inspired you to engineer something really great. So this really inspires me as well. So I typically use this to in many of my presentations. So I hope this was interesting to you all. So now I move on to the next slide here. So as far as, let's say, evaluating the design performance of any product using simulation, there are a variety of different physics that we try to model and then run it. Okay. As far as automotive vehicles are concerned, you will typically see these 5 main physics. To start with, you look at durability. So what is durability? It is basically trying to understand the strength and stiffness of your structure, right? Trying to design in such a way that it can withstand all these typical linear or non-linear loads that is that you also look at what is the fatigue strength. You look at life as well as damage that your structure might undergo because of these different loads, linear or dynamic kind of loads. So that is durability analysis, and typically most of the engineers out there in automotive industry do durability analysis. The next one is vehicle dynamics. Vehicle dynamics is also one of the important physics that engineers in the automotive world run simulations for. And the whole idea is to understand the dynamic loads, right? You basically do a full vehicle simulation to understand what are the different dynamic loads that your structure is experiencing. Handling of your vehicle structure. You look at whether when the vehicle is going through different, let's say, cornering or bends on your road, or through very different terrain, maybe off-roading and all that, whether the ride and handling capability of the vehicle is good enough for the driver to run through the different course. So this is one such physics that we also do. The next physics, which is again a very important physics, is crash and safety. And the whole idea of running such kind of simulations is to understand what is the impact a structure undergoes whenever a car is coming in contact with another car, or it maybe impacts maybe a stationary object. There are a variety of different, let's say, crash simulations that people in the automotive industry do. There is something called as frontal impact, rear impact, side impact, or maybe even a rollover kind of simulations that people typically do in the automotive industry. But apart from that, we also do a lot of other simulations which are related to the occupant sitting inside the vehicle. And that we call it as occupant safety analysis. So this involves basically having to actually model the entire vehicle. And not just that, we also seat a dummy which represents a human body. We build these different dummy models and then have the driver as well as the co-passenger kind of dummy model seated. And once we run through a crash and safety analysis, we try to understand what is the injury that an occupant is going to undergo when such an impact analysis happens. So there are a variety of simulations done for such kind of studies. Also, with regard to that, we also do something called as a knee impact analysis, or what we call as knee bolster simulations. Not just the occupant seated inside the vehicle, there is also a lot of regulations which are basically trying to cater to maybe passengers, or not passengers, pedestrians who are walking on the road. So when a car impacts, let's say, a pedestrian who is walking on the road, what is the kind of impact it happens, and the kind of injury that a pedestrian will undergo. So these are some of the kind of simulations that typically the automotive industry runs simulations as far as crash and safety is concerned. We now move on to noise and vibration. And as far as noise and vibration physics is concerned, it is a kind of a simulation typically done to understand the vibrations that a vehicle undergoes, maybe even the person seated inside the vehicle, because of a lot of these different components which are going to vibrate because of, let's say, the powertrain as well as the road induced vibrations are concerned. So since the powertrain is getting excited because of the combustion which is taking place inside the powertrain, and not just that, there are lots of road induced vibrations, right? Because of these vibrations, the entire vehicle structure tends to vibrate, right? So the whole idea of running a noise and vibration simulation is to understand uh, how is the entire structure vibrating, whether we can reduce these vibrations so that the occupant seated inside the vehicle will experience lesser vibrations. Not just that, we also do acoustic analysis, trying to understand what is the sound level or decibel level that an occupant seated inside the vehicle will experience because of these vibrations. So this is also an interesting physics, and which is really picking up because nowadays people want a less noisy or a less vibrating vehicle these days. So this is an interesting physics that it's become picking up very widely. And then finally, fluid dynamics. Fluid dynamics is one such physics that is going to really affect the design of the vehicle. Why we say that is because, especially in motorsport industry, we basically run what we call as external aerodynamics. And how this external aerodynamics affects the design is that whenever a vehicle is moving at a fast speed, it is going to experience a lot of drag. The drag induced by the air which is moving over the body, right? And the whole intention of running CFD for external aerodynamics is to reduce this drag or lift. So especially in, let's say, Formula One kind of cars, we don't want too much lift, right? So then when it is moving at a high speed, you want lesser lift and lesser drag. So external aerodynamics is again a very important physics that we run. But apart from that, there is a lot of flow and thermal analysis that we do by running these CFD simulations. And this is to basically see how is the flow happening inside the vehicle, but not just that, how is the flow happening around a lot of these structures in your vehicle, which are going to be heated because of components. So CFD is typically done for that. So having understood these, let's say, 5 key physics that we typically run for the automotive industry, let's move forward to really understand what really drives a winning design, right? Peter Wright from Team Lotus had mentioned this in one of his articles here, that driving a car as fast as possible is all about maintaining the highest possible acceleration level in the appropriate direction, right? So how do we actually maximize the acceleration in all these directions? So especially in motorsport industry, this is a very important subject because the whole intention is to drive fast, right? Now, how you can achieve that is by trying to make the car as light as possible. The lighter the car, the faster you can actually go. So the intention is to do a lot of lightweighting on your vehicle to reduce the weight of your structure, right? So this particular aspect of lightweighting is a very important subject as far as automotive industry is concerned, especially in the case of motorsport industry. The second point is to make the car easy to drive at the limits of the traction circle. So if you look at this figure on the right side, this is what we call as a circle of traction, right? You have left turn and right turn on the x-axis, and on the y-axis we have the maximum acceleration and maximum braking. The whole intention is to see to it that your car is easy to drive within given the limits of this circle of traction. So how you can do that is to basically do a lot of these ride and handling kind of simulation, the bad effect of, let's say, running through various kinds of courses that you run through. So this is again a different physics that we really run simulations. The next one is to increase the limits of this traction circle, right? The whole intention is to increase the maximum acceleration or maximum braking, because that is the main intention of motorsport, to have a maximum acceleration as well as maximum braking. So you need a very good powertrain, so and then a good differential, so that you get achieved by having a good powertrain as well as drive mechanism. The next one is to minimize losses. That is drag and friction. And this is basically what we are going to cover as far as CFD is concerned. The whole idea is to reduce the drag whenever you're driving at a high speed. So CFD is one such physics that is going to help you do that. And finally, maximize the power to the wheels, right? So these are the key points which are basically going to help you to get a winning design as far as motorsport is concerned.